What are Pauli errors? How does quantum error correction work? Imagine you are trying to keep a delicate piece of glass from shattering. In the world of quantum computing, Pauli errors are like those little cracks that can form in that glass. These errors affect quantum bits, also known as qubits, which are the building blocks of quantum information. Pauli errors come from something called Pauli matrices, which are mathematical tools that describe how qubits can change. There are three main types of Pauli errors: X, Y, and Z. The Pauli X error is like flipping a coin, changing a qubit state from 0 to 1 or the other way around. The Pauli Z error is different. It alters the phase of the qubit without changing its basic state. Finally, the Pauli Y error combines both the bit flip and phase flip effects. These errors happen for various reasons, such as environmental interference or imperfect control of the qubits. Unlike classical bits, which are more stable, qubits are sensitive and can be affected by noise. The exciting part is that any error affecting a single qubit can be broken down into these specific Pauli errors. This breakdown is known as error digitization, making it easier for quantum error correction to focus on fixing these types of errors. So, how does quantum error correction actually work? The process begins by encoding the information of one qubit into multiple physical qubits. This way, if one qubit gets disturbed, the overall information remains safe. The key here is to spread out the information so that errors can be detected and corrected without directly measuring the quantum state. Quantum error correction uses something called syndrome measurements. These measurements help identify if an error has occurred and what type it is, without collapsing the quantum state. The correction process involves three main steps. First, error detection occurs through parity checks on groups of qubits. This gives us syndrome bits, which tell us if an error happened and where it is. Next, we deduce the specific type of Pauli error and its location based on the syndrome bits. Finally, we apply the appropriate Pauli operator to the affected qubit to reverse the error. Since these operators can undo themselves, applying the same one again restores the original state. This method allows quantum computers to handle noise and maintain stability during calculations. Practical quantum error correction codes, like the shear code or surface codes, put these principles into action, making quantum hardware and software more reliable. In essence, Pauli errors are the basic types of errors that can disrupt quantum information. Quantum error correction cleverly encodes and measures to detect and fix these errors, ensuring that quantum computations remain stable and accurate.